We good? Okay. So hello everyone and welcome. So this is evasion by de-optimization. So first of all, sorry for the last minute title change. Don't get confused. It's the same talk. So I'm going to be explaining how we can use binary code de-optimization for bypassing security products. And before I start, a fair warning. So as you can guess, this is a bit technical talk. So, well, not too much, but ideally you would need some familiarity with the x86 architecture. So if you get lost during the presentation, just hang on tight until the end, and I will try to answer all the questions. So let me quickly start off by introducing myself. My name is Ege Balci, and I'm a cybersecurity researcher. I've been in the industry for around 10 years now, and currently I'm working as a Threat Intelligence Division Manager at Product. And I'm also the author of multiple AV evasion projects. So each one of these projects are designed to solve a specific challenge in the evasion field. And today I will try to define another challenge, and then I'm going to be introducing my own solution. So what is the challenge? So in order to explain what the challenge is, first I need to give you some background information about some basic AV mechanics and current state of the evasion trends. So the first traditional antivirus software is created around 40, 50 something years ago. So it's been a long time. And over all these years, we've developed many sophisticated ways of detecting malware. Currently, we're using heuristic detection with dynamic analysis. We're using some advanced hashing methods, and most products already implemented AI into their engines. So they're using machine learning for classification or similarity detection. But despite all these innovations, if you look at the statistics, you'll see that most detection still happens with rule-based detection mechanisms. So this is generally what I mean by rule-based detection. So each one of these tools are designed to detect known malicious patterns. So these malicious patterns can be on files on disk, or they could be in process memory or in network traffic. So most products in the industry are built on top of these tools. So they have all their own custom signature formats, but at the end, they all use the same fundamental ideas. So in this presentation, we will be focusing on bypassing rule-based detection. So that's our main objective. So a very good way of bypassing rule-based detection, as you all know, is encoding. So we have a lot of encoders available today. 47 of them are already integrated into the Metasploit framework. And we have a bunch more sophisticated ones available on the internet. So what an encoder does is it simply changes the bytes of your payload. So it uses a simple arithmetic logic operation most of the time to change the bytes, and then it also adds a decoding routine. So this decoding routine is a simple loop condition most of the times, and it decodes the payload back to its initial state and executes it in memory. So it's a very, very simple basic concept, but it's also quite effective. So, or it was at least. So the problem is, it is getting harder and harder to use encoders for evasion purposes nowadays. And there are two main reasons behind this. The first reason is simply the entropy. So entropy means the randomness of your code. So when you encode a piece of payload, you produce random bytes and invalid instructions. So entropy rises inevitably. So it makes it very easy to detect. When you attach a process using a debugger, you can easily find the encoded blob just with your eyes. So you only need to check the executable pages with invalid instructions. So this is the first problem. The second and much bigger problem is you have to use read-write-execute memory regions. So this can be considered a very suspicious behavioral pattern nowadays. So when you allocate a read-write-execute memory region, first of all, it indicates a dynamic code. So from the start, it looks suspicious. You might be trying to hide something. And it also very much limits your attack vectors. So there is a thing called ACG, which stands for Arbitrary Code Guard. And it simply prevents you from allocating new executable memory. It's a security policy introduced by Microsoft a couple of years ago. And again, it prevents you from allocating new executable memory. And most signed Windows binaries are starting to enable this by default. So it very much limits your attack vectors. In such cases, you won't be able to use encoded payloads. And finally, read-write execute memory simply is very uncommon. So of course, there are many programs that do use dynamic code, many legitimate programs, but those programs are usually very big applications, such as browsers with JIT engines or language interpreters or Microsoft Office products such as Excel and Word. They do use read-write execute memory, but they usually come with signed binaries. So it's very easy to differentiate the legit use cases nowadays. We also have many memory scanners, such as PE-Sieve and Moneta. So these are considered the industry standard for measuring the evasion score of a implant, of a payload. And these tools specifically check these conditions. They check if you have any abnormal private executable memory in the process. And if you allocate a read-write execute memory region, you will probably get detected. So because of all these reasons, using encoding is not very ideal nowadays. But we don't have to use encoding. We have many ways of bypassing rule-based detection, and obfuscation is also one of them. So when you use code obfuscation, you don't have to use self-modifying code. Also, since you will be producing obfuscated but legit instructions, the entropy should also stay much lower compared to encoding. So at this point, our challenge is very clear. We want to find a way, we need a way of obfuscating binary code without creating other suspicious indicators. So it's important that we need to be able to do this on the binary, because in most cases, you won't have access to the source code. So especially if you're using a private C2 product, such as Cobalt Strike, you will always have access to the binary. You don't get the source code. So since this is an actual challenge encountered by other cybersecurity professionals, there are some existing solutions. And compared to encoders, there are much less binary obfuscators available, simply because it's much harder to implement. I could only find 3 or 4 open source ones. These 2 are the best ones. The first one is Crimson Forge by Spencer McIntyre from Rapid7. And the second one is the Alcatraz obfuscator. So they both work on the same principles. So they take a piece of binary and they obfuscate it using some shuffling, alterations, and they also apply some mutations to certain instruction types based on predefined rules. So there are some problems with the existing solutions. So first of all, they only target specific instruction types. So they're not able to mutate every single x86 instruction. It's quite hard. They only transform certain ones, such as add, LEA, and move. This is not enough for us, because at the end, what we want to do is we want to break as much malicious pattern as possible. And the second problem is how they mutate instructions is creating another recognizable pattern. So here's an example. Here it explains how Alcatraz obfuscator is doing the LEA obfuscation. So it takes a regular LEA instruction, and it first randomizes the memory offset. After randomizing the memory offset, it fixes it by adding an additional subtract instruction. So at this point, it works very well. When you execute this, you will get this exact same result. You will load the same value to the register. But the problem is this will also modify the condition flags. So you want to preserve the condition flags in order to preserve the control flow of the application. In order to do this, Alcatraz obfuscator also adds 2 more instructions. So it adds pushf and popf, and this will prevent the modification of the condition flags. So the problem is the generated instruction sequence is very uncommon. So under normal circumstances, no compiler toolchain will generate these instructions. So this is why it makes it possible for us to write detection rules for it. So when you're writing a detection rule for a binary obfuscator, you will see that it is much harder compared to writing regular rules. When you're writing a detection rule for a piece of malware, you try to try to detect specific instructions with specific values. In this case, you don't know what you're looking for. You can only try to detect certain instruction sequences, so the order of instructions. Because here, in this case, we are looking for a pushf instruction followed by a LEA instruction with any value. It depends on what you're obfuscating. So the operand types can change, operand values can change. So after that, we are looking for any subtract instruction, and then finally a popf instruction. So this rule works because this instruction sequence is a very rare one. It's very uncommon. So if there were no pushf and popf instructions, this would be a very common sequence, and you would get a lot of false positives. So at this point, we want to design a binary obfuscator. We need to avoid using self-modifying code. Also, we need to produce common instruction sequences because of the reasons I just explained. So also, we need to make it look like a compiler-generated code. So it's another good way of hiding the obfuscated code. Also, we need to include most instruction types. So if we only focus on certain specific instructions, we won't be able to break all malicious patterns. And we also need to keep the entropy low. Since we're designing an obfuscator, this shouldn't be a problem. We will be generating valid instructions, so the entropy should stay much lower compared to encoding. So as you can guess by the title of this talk, my solution is de-optimization. So what is de-optimization? It's simply the opposite of optimization. So we will take a piece of code and we will make it larger, longer, slower, but most importantly, we will transform it. It will look different. When you execute it, it will do the exact same thing. So code optimization is a natural phase of every compiler. When you compile a program, the compiler will first analyze the source code, and along the way, on some steps, it will apply some optimization. So these optimizations can be for various different things. You can optimize your code for size. You can optimize it for speed. You can also optimize it for low memory usage, for example. It all depends on your parameters. So these optimizations can be as complex as taking a longer expression and making it much shorter. And they can be as simple as reassembling an instruction to making it shorter. So as you can see, we have different instruction pairs here. So there are multiple ways of assembling an instruction. And as you can see, one is longer and the other one is 1 byte shorter. So this can also be considered a size optimization. So there are some scenarios we want to avoid, but first, yes. At this point, I wanted to understand how compilers work, because what we want to do at the end is the exact opposite, right? We want to take a piece of code, we want to make it larger, longer, suboptimal. But currently, there is no known algorithm that can produce unoptimized code. So there is no way of doing this with a predefined set of rules. So in order to do this, we need to first understand how compilers do optimization. So at this point, I dived into the world of compiler design and coding theory, and there are very good concepts there. Without going into too much detail, I will try to explain my logic here. So in theory, if you can represent a piece of code using some mathematical expressions, you can use certain mathematical properties to influence your code. So here we have a simple example. We have a short piece of code here. You can think of it as a function, a small function. So if you can represent this function as a polynomial, for example, you can use polynomial simplification to reduce the size of your function. So this is the overall idea, and this approach is already being used by modern compiler frameworks such as LLVM, to some extent at least. And what we want to do is the exact opposite. We want to take a piece of code. We will try to express it in mathematical terms. And the good thing about math is you can extend an equation almost infinitely. It's very easy. So, but there are some scenarios we need to avoid. So when you optimize a piece of code, you will see that some instructions change, but some instructions also stay exactly the same. So we want to avoid this scenario, because what we want to do is we want to break malicious patterns, right? There could be a specific detection rule, which is looking for a specific instruction with a specific value. In this case, you won't be able to break that rule. So in order to do this, we will apply the same approach on the individual instruction level. So we need to assign some mathematical operands to specific instructions. So here are some examples. This is very easy to do for most of the fundamental instruction types, such as arithmetics, logics, and load store instructions. As an example, we have move, push, and LEA here. So we can assign this to the equal sign, because what they do is they take a piece of value and they store it somewhere in the memory. So very much like the equal sign on math. So the rest is pretty much self-explanatory, but I'm sure some of you currently think that, but we have many instructions, right? We have around 981 unique mnemonics. So, and some of the instructions are super complex, such as this one, VSM3, RNDS2. Does anyone know what it does? Yeah, I don't know either. So, it's a super complex instruction. It takes around 4 parameters and it does some things. So, as you can guess, it's very hard to represent this using very limited mathematical operands. So my answer to this is, so in theory, we can represent all the instructions, because at the end, the CPUs are built on top of very fundamental logic gates, such as AND, OR, XOR, and most complex instructions are built with combining 2 simpler instructions. So in theory, we can express them all, but we don't actually have to do that. So even if you can handle the most fundamental 20 to 30 instruction, this is more than enough for us. So, because in the beginning of this research, I did a study for calculating the frequencies of each x86 instruction. So I collected around 300 gigabytes of executable files. This was my data set. I collected them from various different sources. For example, I took the default EXEs and DLLs from Windows, and I collected a bunch of ELF and SO files from different Linux distros. These are default binaries, such as find, cat, or the ones you find on a newly installed system. So after collecting them, I extracted the executable sections, such as text sections, because I only want the instructions. I don't want the data parts. And then I simply calculated the frequencies of each instruction. So which instruction is used more. So this is my top 20 list. And as you can see, it contains very fundamental instructions. So move, call, compare, add, jump, XOR. These are very, very generic instructions. And as you can see, in the first place, we have move with 33%. So this means every 1 out of 3 instruction on a typical program is a move instruction. So it is super frequent. So it is generated a lot by compiler. So if we can handle these top 20 instructions, you can effectively transform almost 90% of a program. So, and there are similar studies on the internet. If you scan this QR code, you can easily find one. Some other guy did a very similar study. This chart is his. And as you can see, he also found very similar results. In the first place, he has move. In the second place, he has push, which is on the 9th place on my list. In the third place, he has call, again on the 3rd place on my list. So it very much aligns with my list. So we will be using 5 different approach for transforming instructions. So these are our transform gadgets. And we will be taking advantage of certain very basic mathematical properties, such as arithmetic partitioning or logical inverse or logical partitioning. So, and these transform gadgets are specifically crafted for producing instructions that look like compiler generated but suboptimal code. So this is a super long sentence, but what it means is basically we will use these transform gadgets for generating common instruction sequences. If you generate common instruction sequences, it's much harder to write detection rules. So our first transform gadget is arithmetic partitioning. So this is a very simple one. So there are 2 main ways of transforming an instruction. You can either change the type of an operand, or you can change the value of an operand. That's the two main ways. And in this one, we will try to change the immediate value. So here we have a simple example. We are adding 16 to the AEX register. We can simply represent it as x plus 16. So we will be partitioning the immediate value. So we can say x plus 5 minus 4 plus 2 plus 13. So it amounts to the same. So for the sake of size, we will only partition once. So here are some examples. So this transform gadget will be targeting all arithmetic instructions with the immediate operand. So like sub, add, or move can also be considered a arithmetic instruction in this case. So we will first randomize the immediate value for partitioning it, and then we will fix it by adding a additional random arithmetic instruction. Here we have a example. We are moving some value to the EDI register. We will randomize the value, and then we will fix it by adding a additional arithmetic instruction. So in each one of these transform gadgets, you will see a frequency score, and this score simply means how frequent is the generated instruction sequences. And in order to calculate the score, I used the same data set I used in this list. So I used the same 300 gigabytes of executable files. So this basically means that 38% is super high. So it means one of every three program, one of every three binary generated by a compiler will contain this instruction sequence. So this makes it very hard to write a detection rule for it. Our second transform gadget is logical inverse. Again, this is a very simple math property. So we will be targeting some logical instructions with this, such as XOR and OR. So here we have a simple example. We are XORing a register with the value 16. So if you take the inverse of the first and the second operand, you will also get the same result. So inverse of x, inverse of 16 will give you the same result. So what we want to do is we will take the first operand. If the first operand is a register, we will use the not instruction. And if the operand is a immediate value, we will just directly modify the immediate value with the inverse of it. So the frequency changes between 10 to 28%, depending on the instruction. And even 10% is a super high amount. It means one of every 10 program, every 10 binary will contain this instruction sequence. So our third transform gadget will be logical partitioning. So very much like arithmetic partitioning, we will be dividing some logical instructions, such as shifts and rolls and other variations of those. So when you're partitioning a shift, you will simply divide the immediate value into two. For example, if we are shifting RBX 16 times, we can shift it 8 times twice. So it will give us the exact same result. So if you're de-optimizing the rolls, you can add the size of the first operand to the immediate value. So if you're rolling AEX 10 times, since AEX is a 32-bit register, you can also roll it for 42 times. It will give you the exact same result. So, and this is again very frequent. It's 59%. And this is our fourth transform gadget. So this is offset mutation. We will be mutating the memory offsets. So this is a typical instruction with a memory operand. A memory operand can have multiple values, such as segment registers, base register, a displacement offset, and a scale vector. It's the thing you multiply with at the end. So what we want to do is we want to change the displacement offset, because this changes the instruction a lot. So we will first randomize the displacement offset, and very much like arithmetic partitioning, we will add a additional random arithmetic operation to fix the base register. So here are some simple examples. We will randomize the memory offset and then fix it by adding a subtract or add or other arithmetic instructions. So this is a super frequent transform gadget because it simply targets all instructions with a memory operand. So it has a very, very large scope. It targets hundreds of instructions. And in my data set, all the binaries contain these instruction sequences. So our last transform gadget will be a register swap. And As you can guess by the name, it's a very simple one. We will be swapping the register value. So we will first choose a random register. A typical x86 instruction can take 0 to 5 registers, 0 to 5 operands. There could be multiple registers. We will simply choose a random one, and then we will swap it using the exchange instruction. We will take advantage of the exchange instruction. So again, this is frequent enough. 22% is more than enough for us. And finally, we have a bonus one. So if you remember the list, you'll see that there are many branch instructions there, such as call, jump, or any conditional jumps are on the second place with 9%. So these are like jump less, jump greater, jump 0. These are very frequent because these instructions make up the control flow of the application. And the good thing about binary obfuscators is when you add even just a single bit to a binary, you misalign all the memory offsets. So in each iteration, every time you add a new instruction, you need to fix these branch instructions. So when you add a new instruction, in this case, for example, you need to jump much further. So in every iteration, we need to fix these branch operations. So in other ways, they are getting obfuscated automatically. So it's also very good for us. So at this point, I have successfully implemented the optimizer. It's currently operational. In this demo, I will show you a simple scenario. So here we are creating a very generic Meterpreter reverse TCP shellcode from Metasploit. And we will be de-optimizing it using the tool. So yes, this is the tool. You have to specify the architecture and the bitness of the binary. Currently, it only supports shellcodes. So here it quickly de-optimized the binary. It also tells you which transform gadgets are used. So you can specifically choose a specific one for the optimization. So if you give the verbose option, it will also give you a instruction diff, so that you can easily see how it is transforming the instructions. So as you can see, it changes a lot if you use all of the transform gadgets. So now we will simply, I will show you the binary diff of the original shellcode and the de-optimized version. And as you can see, the red ones are, it means changed. So we almost rewrote the entire payload. It's also much longer since we are de-optimizing it. And now we will simply compile a simple shellcode loader for running the optimized shellcode. So we will transfer this exe file to a Windows box. Yeah, we will run it. And if you look at the below part, you'll see that it is functioning as intended. So it is much slower, obviously, because it is de-optimized. But as you can see, the Meterpreter is functioning as intended. So when it comes to the detection rate, it's very hard to show you some meaningful statistics about this. But when you scan the original shellcode without any encoding, you'll see that it is getting detected around 18 to 30 engines. After the de-optimization, it drops to 0. Of course, this is solely by static detection because we're uploading a binary, not an executable file. So as I said, it's very hard to give meaningful results because we're only focusing on static detection. When you run a payload, many things happen depending on your malware. If you're running something super suspicious, there are other factors at play. And of course, there are some known limitations with these methods. First of all, the scope is limited, as I explained in the beginning. There are some instructions that do not take any operand values, such as NOP or POP-F, PUSH-F, AAA, CLD. So these instructions do not take any operand, so it's not possible to mutate them. Only thing you can do is you can move them around, you can change the order of them. But this is not a very big problem because, as I said, if you can handle the fundamental instructions, then that's fine. Also, since we are producing new instructions, the the delta, the distance between these instructions are always changing. It's also can be considered another obfuscation. So second known limitation is self-modifying code. Currently, this tool does not support any self-modifying code. So if you try to de-optimize a encoded payload, for example, it will probably break. So this is kind of impossible simply because there is no way of predicting the execution flow of a program without actually executing it. So we won't be supporting any self-modifying code. And another known limitation is code with data. So this is not actually a limitation. So in some cases, you will have some data in your code, such as some shellcodes contain some strings in them. Since this is a code optimizer, code obfuscator, you need to skip those strings. If you don't, the tool will corrupt them. There is an option for skipping offsets. So you need to skip these ones. And finally, overlapping instructions. So this is again a super rare case. In some situations, some compilers do produce overlapping instructions simply because saving up some space. So best way to explain this is with an example. So here we have two move instructions and then a add instruction. Then we are jumping 10 bytes back. So when you do this jump, you land in the middle of the first move instruction. So when you land there, it changes the instruction. So this is a clever way of saving up some space. This is a size optimization. So in this case, if you try to de-optimize this, it will probably break. But as I said, this is a super rare condition. So the tool will be available at this address. Go ahead and follow me on GitHub. It is fully written in Rust. It has no external dependencies. And I've used the x86 disassembler library, which is super cool. I advise everyone to use it. So, and in the future, I will try to add more support for example, more complex file formats. Currently, it only supports shellcodes, but in the future, you will be able to give PE files and ELF files for de-optimizing the text section, for example. And I will also try to add new architecture support, such as ARM and RISC, because simply the industry is going towards that way. So this was it. Thank you all for listening. If you have any questions, you can ask now, or you can get my contacts here with this QR. Is there any questions? Oh, there's one.
Thank you for the great talk. I was wondering about because this whole idea breaks the pattern detection, right? But doesn't it create a sort of a new avenue of detection, which is the statistical one, right?
Yes.
Because the statistics of the instructions now changed between the original binary and the other one. So have you considered somehow trying to tailor this so that the de-optimized version still follows the statistical distribution of the, let's say, of the original binary, or how often the certain instructions appear?
Yeah, great question. So, of course, this will create new ways of detecting these methods. But if you think of it that way, this way, so you can, in theory, you can disable all optimization on a compiler, right? In that case, compiler will produce similar code, so similar to this one. So if you find a way to detect this, you will also detect those ones. So it is creating kind of a dilemma. So yeah, that's how it is.
Thank you.
Thanks for the talk. So I was wondering, because you said there are like 981 unique instructions in x86.
Yeah, mnemonics. Yeah.
Actually mnemonics. Yeah. So actually, did you maybe check like how many of those unique mnemonics you could find in those 300 gigabytes binaries? That's my first question. And the second one is, did you also consider disassembling in between instructions as well? Yeah.
The frequencies I show on the transform gadgets are not all of them are specifically to that sequence. Some of them are matched because there are some patterns in between instructions, just like you said. And Yeah, there are. My data set was very limited. 300 gigabytes is not that much, as you can guess. But most of the binaries I used are benign and default day-to-day, everyday binaries. So if you do this study with, for example, OpenGL libraries, so GPU code contains a lot of complex vector instructions. In that case, you will get a lot different results. Yeah. So this will be at the end. This will be an open source tool. Everyone can try to find ways to detect these sequences.
Okay, thank you.
Yeah.
Thanks for the great talk. Did you have any problems with the flags not being preserved correctly?
Yeah, great question. I normally explain this, but it takes a lot of time to explain it in the slides, so I removed it last minute. So each one of these transform gadgets are designed specifically to preserve the condition flags. There is only one that it does not. In that case, the tool is doing some tracing on the binary and trying to decide if that instruction is crucial for the execution flow. So if those condition flags are required, then the tool will skip that instruction, or it will try to de-optimize it with another transform gadget. So I paid attention to that detail.
Okay.
Yeah.
Okay. So you just look for conditional jumps after that.
Yeah.
Thanks.
Thanks a lot. Also, it was a lot of joy, and I could see maybe some Can Yıldızlı effect, like, because presentation was very
thanks.
structured.
Thank you very much.
And thanks to him as well. A few maybe quick questions. Security applications are moving into Intel's, for example, new instruction set extensions with SGX and TDX, and they are implemented with Zoo code, and they follow, like in the threat model, they consider everything of those world untrusted, and then the trusted secure applications are being programmed with Zoo code instructions. Would you also explore that aspect, that in terms of considering these new programmable instructions, they are not on the microcode or hardware level, but more of the dynamic instructions coming up and being added in the new stuff? That's the first one.
Okay. It was a very long one. I hope I can remember after the second one. Yeah.
The other one is, like, we are adding here, if I understand correctly, some artificial random level of entropy.
Yeah.
And did you ever think of detecting that static pattern? Would it be a static property because the tool is available? Now, if we try to reverse engineer your tool, would it be then, like, can we get basically a certain non-natural pattern out of this artificial addition? Or
Yeah, for the second question, yeah, it makes sense. And all the meaningful metrics come up after the release of the tool, usually. So we will see. I mean, this is a never-ending cat and mouse game. So we will see. Maybe people finds a way to easily detect these sequences. And for the first question, I think you mean like SGX, right? Trusted computing, but you mean?
Well, yeah, TXT, all the SGX stuff and TDX stuff, they're coming up, and I was wondering, like, I think it could be also not exactly in the scope. So I'm aware, and I'm really thankful, like, you put the scopes so greatly, and to-do, it was like perfect to see all these maybe polymorphic, metamorphic aspects as well. Like, it's great coverage. But I was wondering, like, how much it would make sense to extend there. Like, it's not necessarily would you extend or not, but maybe we could catch up after. I don't want to take too much time.
Yeah, it's a kind of complex question. I have to think about it. Maybe after the talk. Yeah, let's meet.
Thank you. Thank you for the great talk. On one of your slides, if I remember correctly, you mentioned something that you called partitioning.
Yeah.
Where you would have, you would transform a shift left into two shifts left with the same register.
Yeah.
And you said that those instructions were present in almost 100% of the binaries.
Yeah, it seems weird, right? Yeah.
Yes. I just can't wrap my brain around the fact that compilers who are trying to make the code as optimized as possible would make the same instruction twice, essentially. So my question is, when you looked at the the frequencies for those instructions, did you take into account that they were using the same registers? And if yes, do you have any idea why the compiler would issue such code?
Yeah, great question. So it's not on all of the binaries. It's around 59% for this specific case. And
sorry.
I know it seems weird. No compiler, again, should not produce this double shift, but this happens because of there was someone asking about the in-between instruction. So since shift instruction is a very small instruction, it's 1 or 2 bytes, when you write a detection rule for this specific case, you're getting matches for the in-between instructions. So there are much larger instructions that contain this 1 or 2 byte. You're getting, at the end, you're getting false positives, but it also helps us at the end. Yeah.
Okay, thank you.
Yeah. Okay, I think that's it. Then I thank you all again. Enjoy the conference.